Okay, let's start the class number 14, and today is the 24th of February 2020. In the last class we finished up the derivations of the quadrilateral elements. I explained you the architectures of the functions, and the first functions we talk about is the function eval. Okay, so the variables names are already explained in the last class. So dndc means the derivative of shape function with respect to the local coordinates. Variables dc dx, that includes dc dx, dc dy, the eta dx, d eta dy, and JCB stands for the Jacobian of Transformation. So the function eval needs the c value, eta value, element type, and element xy coordinate. That will be from the outside. We will provide the xy coordinate for such at the outside. Okay, so we prepare some explanation a little bit. dndc stand for the derivatives of shape functions with respect to local coordinates. And dc dx is the derivatives of local coordinates. Just made it. Derivatives of local coordinates with respect to global one. JCB stands for Jacobian of Transformation. Derivatives of shape functions with respect to local coordinates. Okay, right. So for this I have the if, and inside the if type is equals to 4, for example. So if the element type is equal to 4, I will define the dndc being zeros, 4, 2. Likewise, else if e type equal to 8, the ndc is going to be zeros, 8, 2. Else if element type is equal to 9. I'm not sure if do we need semicolon there on the back? Maybe not. I will just check one little by little. And if dndc is equal to zeros, 9, 2. Okay. And then we will define, right? dn dc something comma something is equals to something. Copy, and we have in total 8. So we start with the 1 2 3 4 and 1 2 3 4 derivative with c c c c eta 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 and eta. Okay, so we just check out the derivative of Q4. So the first one is equals to 0.25, which is a quarter multiplied by eta minus 1.0. Alright, and basically it just looks like this pretty much. Copy and paste. For number 2, 1 minus eta, so I put the negative there. For number 3, 1 plus eta, and for number 4, minus 1 minus eta. Okay, so I put it this way. Done. And derivative with respect to eta is 0.25 c minus 1. Then we move over minus c minus 1. We move over 1 plus c, and we move over to the last one, 1 minus c. Put the negative side there. Done, right? So what else? Still 8 and 9. Don't put it there. We will find, we found the NDC already. Then we're gonna need the Jacobian of Transformation and dCdx. Okay, so in order to get the Jacobian of Transformation, then we're gonna need derivative of the global with respect to local, and that is actually equal to the global one is just 4 by 4. Okay, I didn't define, so I make it dx dc dx d eta dy dc. Alright, we got dc dx. Okay, then dy d eta. Okay, you just make it et then. So dx dc is a summation of x times dn dc. Okay, so where's the x comes from exyc, thus I can make it this way. For I equals to 1 to etyp element type, and then the x dc is equal to dn dc index I comma 1, okay, times exy co, and xy coordinate has to be for the I comma 1. The I is the element I, comma 1 is the x, okay, the node I and x coordinates. Next one, so basically there I just put 0.0 to initialize the value. dx d eta is equals to still dn dc times that is comma 2, right? So derivative of local coordinates with respect to the comma 2, note I means shape function I, comma 2 means with eta, multiplied by exy, this is comma 1 because you are talking about the dx, and next dy dc and dy d eta, and I paste down c y, that's comma 2, and then comma 2 and 2, right, with eta, so it is comma 2 here, with c is comma 1 there, but both element xy coordinate must be comma 2. N4, okay, now you get the x dy with local coordinates, and we can find the Jacobian of transformation JCB for this integration point is equals to dx dc times dy d eta minus dx d eta times dy dc. That's it. And then you get the derivative of c and eta with respect to x and y. So the data structure was shown in the PDF of the last class. The row number, I'm going to explain a bit. The row number is for x and y. Okay, row number for x and y, column, how many rows? Okay, row number for x and y, column number is for c and eta. Okay, so start with the dc dx 1 comma 1 is equal to dc dx, which actually this one is the dc the real dc dx. dc dx turns out to be 1 divided by JCB, Jacobian of transformation, multiplied by partial derivative of y with respect to eta. Okay, that's it. Next one, dc dx 1 comma 2. 1 comma 2 is 1 over JCB times minus dy dc, which is, this one is d eta dx. dc dx 2 comma 1 is actually equal to 1 over JCB times minus dx d eta. This one is equal to dc dy, and the last one dc dx 2 comma 2 is 1 over Jacobian transformation times dx dc. Okay, which is dx dc, which is the d eta dy. Okay. Now we have the dndc available, dc dx also available, Jacobian of transformation available. That's it. And then I say return because I don't want to do it all here. Return. Okay, and if, and then in function. So name is eval. Okay. Evaluation. The next one. Yes.
What does it mean, return?
Just stop. I just don't fill in the thing. It is just the simple routine if you can differentiate. So yeah, if you can differentiate things correctly, then the thing will be the same. So for over here, it's going to be working this way, all right? And JCB. Actually, this part here can come after, right? Because it is common. So this is for the element type, and then this part here, element type is equal to 4, so this part here is actually can be outside the if. So we initialize the value. This is going to be working with everything with all the if. Okay, all right. And once you get the NDC, then it comes out and we can use them in common. So it turns out to be 4.2, 8.2 or 9.2. It comes to here, it is generalized here to E typical, and then operations going on over here, it takes EXY from outside and then come down here to close the for loop, can find Jacobian of transformation for this given C and eta point, and then the derivatives are readily calculated down here, and that's it. Okay, so nothing tricky. Save it. Which one? DXDC, yeah. Oh, yeah. Sorry. Yeah, thank you. So it accumulate. Yeah, thanks. DXD eta accumulates. Okay. DYDC. dy d eta plus. Okay, thank you. Yeah, so we set 0 first, then we accumulate up the values for e tip times I times, okay, xi d and dxi. All right, save it, and we come to the function main. For time being, I think I will just give you the, what is it now? What is the name? EXYZ. EXY coordinate is equal to make it easy, 0, 0, 4, 0, 4, 4, 0, 4, close the bracket, and there you go. We have element xy coordinate. We are going to for I equals to 1 to NELE NELE is a number of elements. ETYP is the element type. 4 stand for Q4, 8 stand for Q8, and 9 stand for Q9. Basically the coordinates xy of the nodal points will be constructed using the mesh generator. We will be constructing the mesh generator after this. We're gonna construct just the rectangular mesh and triangular mesh. Actually the mesh issue is a long issue as well, so you can spend like hours and hours to talk about the mesh algorithm, mesh generator, and the control of the mesh, because you cannot just mesh the domain up. The mesh, the shape of the element does affect the quality of your computation. So the quadrilateral element we derive over here, they are majorly made for the shape that is pretty much like the square. If you see your element in the numerical domain, it is -1 to 1, -1 to 1, and the shape over there looks pretty much like the square. So basically, if you can maintain the aspect ratio of your physical domain element to be as square as possible, that will be the best, because it maps well. Distortion from the physical to the numerical is not much. Well, once we are back onto the iPad in some class, I should draw you and show you some element that will not work for us. For example, if the aspect ratio between two sides are like far away from one, well, 2 is still doable. 0.5 is another side, right? Okay, so 0.5 or 2 are the same thing. So one side is short, one side is long. Long side to the short side is ratio of 2. Okay, still usable, but not as good if it is like closer to 1 to 1. But when you go for longer, like 4, 5 to 1, like that, then your physical domain element looks like a strip, but your element in the numerical domain looks like the square. So the performance will not be as good, or you have too much distortion. For example, the angle of the element, it's not close to 90 degrees. Well, it has some tolerance that your discretization might not be a perfect square. It could be like some angle, but it shouldn't be like the very sharp angle. something which is far away from 90-degree angle, that is not the good discretization or good matching. And generally the issue comes because your domain is irregular. You are not analyzing just the square or rectangular shape domain that is possible for you to do just the grid, like the table grid discretization. We analyze something which is much more complicated, so that results in the distortion in the mesh and some sort of bad mesh shape, geometry of the mesh might not be so good when you finally finish up. Generally the algorithm will do this job for you, but you should look into this, and actually the algorithm is gonna report you the condition of the mesh. So in some cases that some of these elements with the strange aspect ratio too extreme, okay, too much, too long, the difference in aspect ratio or the angle, the distortion is too much, the program is going to report you at the end of the matching routine. So it tells you that you might need to look into this matter, or if you are not so serious about it, then okay, you skip it. If the element like this locates somewhere that you do not expect probably the large strain, large stress area somewhere far away, well, it's not good to contain the element like this. It's not always good, okay, you know that this is not a good thing, so the best is to eliminate it. But if you cannot, and if it might not look too bad, then okay, you can leave it there. But if it is in the critical zone, for example, if you have the stress concentration, if you need the very good result, good accuracy from that given location, and you have this bad mesh geometry over there, then remesh. And generally, if you make the mesh size smaller and smaller, that is the way to resolve the issue. Like I said, the point is that the smaller the mesh size is, the more expensive your computational will be. Okay, so it is something that it is like using money to resolve things. You add more resource, you add more money, you spend more time, then okay, you get the better outcome. But or you might consider the local mesh generation. So you might do some sort of like zoning your domain. So your domain might be a big piece, then you zone it, okay, zone it up. Well, that will take you some time or some idea to set up the zone. So some zone you can control the mesh size to be small, whereas the other zone could be bigger as it can accommodate your requirement still. Okay, so mesh that we will write up the code in this course will be just a simple rectangular mesh. For the other kinds of mesh, there will be a lot of subroutines and algorithm used to construct. But for you as a user, you mesh the domain, you look at it, you should be able to tell that if you need further elaboration on the mesh, or if it is good enough for the analysis you are going to conduct. And 10 different people will end up with 10 different mesh. Okay, you have uncountable possibility, and in fact it is infinity possibility to mesh one single domain. So different people come up with different solutions, but the thing is that who end up with the right one. This is the bad thing about the use of the computational mechanics program, that you always end up with the result, but people in this class ends up with totally different result. You do not duplicate the result. Well, if you are not doing the homework, mesh is not given, you will mesh up things for yourself, and then at the end of the day you end up with different solutions, and that is scary, right? I do it this way and do it another way, two different solutions. This is why the course like this is also important, that to make sure that you use the program and you know how to find out if your solution is appropriate, if it is correct or not. That is the important thing. But if you just care about, okay, you just need to run, you need to get output from it, and you don't care what it is, right or wrong, you just get the nice color contour like that, well, you risk yourself. Okay, so here you can see the loop. Loop over the element. This is necessary. It is like the computer method class that we have. I don't know how many elements you have in your system. You are going to construct the stiffness matrix for all single elements, right? So we have the loop for I equals to 1 to NELE. That's a good first step. What is the next step? Since we are going to do the numerical integration, we are going to have the loop over Gauss point. So you have the for j equals to 1 to NINT. Now let's define the NINT. NINT stands for the number of integration point. And we have the 2 and 3. This is for in each direction. In each direction. Then there will be something that we use to some little subroutine, okay, call it this way, some little subroutine that we call it, and then it return the value of x and of c and eta, okay. So I'm gonna call that function like a Gauss, but what we get in return is the c and eta. And another thing is the weight of the integration, WGHT, and that is equals to, I call it Gauss. We need two things. We need an INT and we need the J. We need an INT because when we call this subroutine, we need to figure out 2 or 3 points, so it's gonna return you the right c and eta and weight. Okay. Then I make a new one function, c eta and WGHT weight equals to Gauss. Gauss come from what? NINT and J. Okay. So if NINT is equal to 2, basically over here, that's gonna be the nested loop. J and K equals to 1 to NINT. Okay. And it has to be J and K because you have two directions. Comma K. If NINT is equal to 2, okay. What will be the shortest possible code? Actually, another thing, it could be 1 point also. NINT equals to 1. J is for, okay. If J is equals to 1. Not necessary for 1 point integration. You don't need to think much. C is going to be equal to 0.0. Eta is going to be equal to 0.0, and also the weight is equal to 2.0. That's it. Else if NINT is equal to 2, and then we're gonna need another if inside. If J is equals to 1, if J is equal to 1, J control is C, so C is equal to minus 0.57735 02691899626. That's it. 57735 02691 and 89626. Okay. Else C is equal to the same thing, different sign. And if so we finish up the if for the J, we will have the if for the K. So change from J to K. I don't like this. I don't like this. I don't like this. Let me see eta. Let me call it from The operation like now is that it has to come into this and then go through many if, and that is going to consume my computer time. I do not want my computer to be exhausted, so I just call this guy out there. I do it this way then. Call it out there. Alright, I don't care about JK. I just call Gauss and this thing. That's it. Right. And then the Gauss is going to return the vector or the matrix of this C turns out to be big C eta. Okay, and the weight. What I did, it's not wrong. It will work, but I just don't like it. It will be slow, too slow. I am picky. So C turns out to be 0s, 1, 1. And eta, it turns out to be 0s, 1, 1. Like as well. So, and inside is a 0 already, so I don't need to mess with it. And then this is 0s, 1, 1. So WGHT 1, 1 is equal to 2.0. That's it. Okay, that's the first one. Second one, if the integration point is 2, then copy this stuff. C is equals to 2, 1, 2, 1. Weight is also 2, 1. So I don't need to do all this if. But the thing is that I need to define C 1, 1 is equal to C 2, 1 is equal to eta 1, 1 and eta 2, 1. Weight 1, 1 and weight 2, 1. It's all about the data structure and architecture of the code. C eta weight will be 1.0 and 1.0. Okay. Right. Else if NINT is equal to 3, again run it this way, copy and paste. Turns out to be 3, 1, 3, 2 and 3, 1, 3, 1, 3, 1, 3, 1. Oops, undo, where's the undo? Okay. Shift N. Two, 1, 3, 1. Actually, coding teaches you many things. This is one thing. Before you do something, you look all the way to the end, and you know what you are going to do there, and then you do this in this way. So you sort of try to foresee what's gonna happen in the next 2 or 3 steps, and then you do the first step right. But if you do first step just the sake of doing the first step, that's also applicable for life. Do the first step just for the sake of first step, then the second step could be messed up because you don't plan for the second step or third step and fourth step. So the more you grow up, the further the step you can foresee. So you can look to the step number 5, 6, 7 and then do the step 1 accordingly. You know you have to do the step 1, but how to do step 1 or which way? Okay, you can design step 1 to accommodate the end step in your life and also the end step in coding. Well, and that is the ability to survive in the world well. Applicable to everything: interpersonal issue, the work issue, computational issues, etc. If you anticipate the consequence of your action before you do everything. C is for 3 integration point 0.77459 66692 41483. This is the first. It is a negative sign. Copy and paste negative sign as well. So the middle point is basically 0.0. That's it, 0.0. And regarding the weight, so for the 0 point you have the weight 0 point 1 2 3 1 2 3 4 5 1 2 3 4 5 1 2 3 4 5. That's it. 0 point 1 2 3 4 5 6, and that's the same thing. Okay. Alright, we can accommodate 1 point, 2 points, 3 points in one direction. And if so, once you call this function, you're gonna need just to call this one only once at the Gauss at the very beginning over here. So once you call, then these numbers are available for you to use. When you do, well, these numbers just a small vector, small matrices, so it does not consume your RAM much. It will be there in your RAM all the time. Once you call the function main, it will not disappear. But for something that is like gigantic, like the stiffness matrix, when you write the code, if the stiffness matrix has to be recalculated, or something that is big and needs to be recalculated, and you want to free up your storage, so you need to deallocate. The function like that is possible in program like Fortran. Actually in MATLAB could do that, I guess. But it is just the way you manage your storage, your usage of the memory. You don't want to keep the large piece of information in the RAM. Okay, so the sooner if it is possible, you free it up, then you can see the drops in your RAM. If you look at the task manager and monitor the memory, you can when you run the big program for finite element program, you might look into that task manager a little bit. Don't open it all time. You open it up to see Okay, CPU is used this much, let's say 25%. If your computer is super high spec computer, you might use 25 CPU, RAM might be 50% or 40%. You know that you might do another analysis in parallel, because if you don't intend to play Facebook there, then you use another part, okay, the remaining part of the core of the CPU of the RAM, which is not used yet, for another analysis. So you can run two analyses at a time. We might have 8 gigabytes, 16 gigabytes RAM. That means more than 2. It could be 3 or 4. But to be able to plan, to run the analysis, you need to look at the task manager to see the performance, the usage of your resource a little bit. In my time, 4 gigabytes seems to be so cool, or 2 gigabytes seems to be. I don't remember the computer I used to run my Finite element code. Yeah, these days it's much bigger space, much bigger memory, so you can run more with less time. So this is not a big deal. You don't need to free up. You just let it float around. See eta and weight is floating around. The point is that we are going to have two nested loops that nest over the integration points in each direction. So you have the integration point in C direction, and also the eta direction. So just for explanation, thus the C is going to be equal to C J, 1. Eta is going to be eta K, 1. WGHT, the weight of integration. I make it the WGHT, okay, is equal to weight of integration in the J direction times WGHT in the K direction. Remember that in the last class I expand the term, okay, in your integration, double the integration in x and in y of the function inside dx dy, and then I, how to say, expand it and I approximate it using the Gauss quadrature rule. So it turns out to be summation of the function inside, which is the B transpose dB, multiplied by Jacobian of transformation, multiplied by the weight in C, and multiplied by the weight in eta. You have two weights multiply. Okay, so this weight is like a lump weight. So this lump weight for a point, okay, one point that consists two different directions, is going to be the multiplication of weight in C and weight in eta direction integration. Now, the next step is to call the eval. So I just do it here, copy and paste there. So eval is in place. Okay, the eval needs the z and need the eta. It does not need the weight. Okay, e tip will be there already. Element type, this is the information we give it ahead of time. Element xy, I just give the temporary element xy. Later on we are gonna have to put the mesh generator in there. So exyc will be taken from the global nodes. So that will be like the xy coordinates of the code in structural analysis. XYCO. Previously we had that. We're gonna have nmap again. The mapping of the nodal point to element will be the same like before. So the architecture of the structural analysis program and finite element analysis program are pretty much alike. They are not different. The difference is just the procedures inside here that is used to come up with the stiffness matrix or force vector for each type of element. That will be the only difference. Okay. Now, at this point, we have dn, dc, dc, dx, and Jacobian of transformation. And we recall that the B matrix, we are ready to construct the B matrix out of this given information. So the B matrix, I'm gonna make it for I, j, k, l equals to 1 to e tip. I mentioned in the last class that the nature of the B matrix, it looks repeating. So the cells is going to repeat for E type times. N4 you have 4 and so on. So the B matrix is then initialized for zeros. How many? 3, 2 times E type. Basically, this should be outside, sorry. So initialization starts like this, and then we start computing the value inside the B matrix. So in each cell you have D phi dx. So the B matrix, what is the entry? Actually, I talk about that. The x, the row is 1. The column is 2 times L minus 1. This is for d phi dx. So I make it here d n dx. And d phi dx turns out to be d phi for the shape function with respect to x. So d n dc, what will be the index? The index should be L for a shape function L, and with respect to c, so comma 1 multiplied by dc dx, dc dx, dc dx. So with respect to x, it has to be 1 comma 1, the dc. Add up with, I think it's gonna exceed number column 1, 2, 3. Yep. Add up with dn dc of the L again, but comma 2. Derivative of phi with respect to eta, and then times the d eta, which is dc dx eta with x. So start with 1 and comma 2. That's it. So let me point it out. I zoom in for you. This part here, L comma 1 is the d phi L with respect to 1 is a c. Okay, and this piece here is the dc. This comma 1 is the column index is for the c with respect to x. Down here, this is the d phi, d eta. The d eta come from 2. The phi is the phi L, which is this one here. And here is the d comma 1 with respect to x, but comma 1 is respect to x. 2 means the d eta. So d eta dx. Turns out you get the derivative of function, shape function with respect to x. Second, B matrix 1, 2 times L is equals to. So this one is not 1, sorry, 2, 2 times L. This one is for strain epsilon y, which is d with respect to y, right? So d phi d must be L, 1 first times d c dx must be y, which is 2, 1 plus d and dc. What is this one? L, 2. Okay, for eta dc dx, and then y and eta. Okay, so that turns out to be d n dy. Last, not last, B matrix of 3, 2 times L minus 1 equal to. So this one is actually equals to the B mat of 2, 2 times L. And B mat of 3, 2 times L is equal to B mat of 1, 2 times L minus 1. So this is equals to the top one. This one is equals to this one. Alright. What else? That's all, right? We have just 4 entries which are non-zero. The rest are 0. N4. So right now, you construct the B matrix. This is pretty fast. We are right now close. So, well. Outside here, I have the KELE then defined as zeros. 2 multiplied by E type, 2 multiplied by E type. Okay, so element stiffness matrix which then defined already. Actually, this has to be redefined every time I cut it. It shouldn't be there. It should be before the calculation there. Okay, why is it there? It is, well, undo, edit, undo first. I paste it here then. Okay. Why is it there, this line? Because every time you calculate, when you change the element, you need to reset the KELE. The nature of this work done, we are inside the integration loops. So loop in C, loop in eta, my KELE. The summation, we have summation in C and eta. So that's going to be equals to B mat transpose multiplied by D matrix, okay, to be defined, and then B mat, right, multiplied by the weight. I call this one what is it, NWGT, okay, PWGT, point weight, okay. So this is for this given point, PWGT, okay. What else? We have the weight. So actually we don't really need to. We just cut it here and paste it there. So I don't need to introduce another variable. Okay. Fine. So weight are taken here. B transpose DB. We need the JCB, Jacobian of Transformation, must be there. And then you want to accumulate. So K ili, okay, mount is equals to K ili itself as it accumulate. But before it starts the accumulation, before we come into the loop, we reset the KELE out there to make it 0. So when you come to the next element, it does not carry the values from the previous element and accumulates further and further and further. Now KELE is equal to blah 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 blah. All right. N4 N4. The point is that after this part here, then it is the plugging in. So you will use the same technique in the computer method. If you recall that way, I just take every single entries in the element matrix and migrate them to the system matrix. We will do that. But first of all, before we go so far, we're gonna fix the bug that are in here first. There will probably be some, or not some, might be a lot. Close all, clear all. Okay, I don't input anything there, so ultimately I need to see KELE. I think I need to define the NELE here equals to 1 to make it run. Save it. Main. See. Okay. Maybe we shall. Oh, I don't need the JK here, right? Okay, I save it like this, otherwise it's gonna bug out there. Okay, so as soon as I plug in the NRNT, I'm gonna get, I take the semicolon out to make it work. Alright, and this moment I hate main. Okay. What? NINT? Oh, okay. I didn't define NINT. Well, 3. Okay, I didn't put the dmat file later. So NINT 3 points, it gives this out. I need the format to be long. So I can see C is returned, eta is returned, weight was returned, dmat is not given. Okay, so D matrix. Dmat is equal to zeros, 3, 3, and dmat comma is equals to something. Okay, home. There are 5 non-zero. Start with the 1, 1, 1, 2, 2, 1, and 2, 2, and 3, 3. That depends on your type of plane problem. So elastic modulus must be defined. Okay, let's say 100. PRTO, Poisson ratio, is also defined 0.2. And then rigidity matrix for plane strain. So if it's a plane strain, plane strain. Okay, lambda plus 2g. Okay, let me check. So lambda plus 2g is equals to E mod multiplied by 1 minus Poisson ratio, and then divide this by 1 minus 2 times Poisson ratio times 1 plus Poisson ratio. Okay, so this is the lambda plus 2g. We need lambda also, which is elastic modulus times PRTO, Poisson ratio. Divide by, copy this, and then dmat 1, 2, dmat 1, 1, and the last one is the G, right? Shear modulus, which is E mod divided by 2 times 1 plus PRTO. That's it. Okay, then we have the rigidity matrix now. Oh, okay. It comes out, and this is for Q4. Let me just play with this a little bit. This is 509 blah blah. Okay. There you go. Back. Actually, the Q4 two integration point surface. So let's see. I copy this then. So 2 point and 3 points should return us the same thing. Okay. Well match. If you want to check if something match with another thing, easiest way, this minus this. 1 2 3 4 5 6 7 8. Okay, the mismatching is to the minus 14 power, like that, very small. Okay, so these two are identical, but still it does not say anything that it does not guarantee us anything that our element is correct. I mean, how do you know that physically this stiffness matrix is correct? So we have to test it. The easiest way to test the stiffness matrix, just apply the easy force that you know the solution already.